So let's look at the same sort of example that we had in the previous clip. So we'll have the temperature given by some function f. And so this will still be a function on R3. So it's assigning the temperature at points in space. But now we will consider that we can't fly through space anymore. Instead, we have to live on a surface. So we have a surface which is going to be parameterized now by a couple variables. We'll call them u and v. And so there'll be an x coordinate as a function of u and v, and a y coordinate as a function of u and v, and a z coordinate as a function of u and v. Okay, and so now S is a map from R2 into R3, and it's giving us some surface. So imagine that it's actually parameterizing a sphere for us, and then we can think of this as being us living on Earth. There's an oversized me. And so then we have some axes, and I can continue with this metaphor of using different colors to indicate different values of temperature in R3. So suppose this is giving sort of what. So here's what the values of f look like. So I'll do something. Here we go. Okay, so here's sort of a temperature map showing how hot different parts of the globe and surrounding atmosphere really are, right? Now, the thing that differentiates this example from the previous one is that in the previous example, there was a curve and we could move forward or backward along the curve. Now we can change the u variable, which might make us move in that direction, or we can change the v variable, which might move us in some other direction. So let's see, this is depending on v and this is depending on u over here. So the key difference now is that we can look at the change in f as u changes or as v changes. So if we want to look at the change in f as u changes, then this is going to be the change in f with at the rate of change of f as x changes times the rate of change in x as u changes, and then we have df dy, dy du, and df dz, dz du. Now the only difference from what I wrote for curves previously is that now you notice that these are the curly d's because they are partial, because x and y and z are now each multivariable functions. So when we take the derivative with respect to u or v, those are actually partial derivatives. But that's just a notational thing. It doesn't really mean anything significant. So we have that, and then we can also talk about what happens if we change the latitude and go north-south along the blue line, and that's looking at the rate of change of f as we change v, right? Changing du, that apparently the way I've drawn it, that changes the longitude as we go sort of east-west around the globe. And so then this is going to look exactly the same. So I'll just duplicate it there to make it look the same, except that instead of having u's along the bottom, we have v's along the bottom. Yeah? And so once again, it's worth noticing or pointing out that these take the form of dot products. So it's gradient of f dot, and then so derivative of u with respect to x, y with derivative of x with respect to u, y with respect to u, z with respect to u. That's actually the derivative of s with respect to u. And then similarly, we have dot product with dsdv. And this is just a little side note for those of you that are going to go further with mathematics. This actually comes from matrix multiplication. So if we look at these, say we take this to be a vector with two entries, this is actually where we've got the gradient. So again, that's df dx, df dy, df dz, and we take the product against dx du, dy du, dz du. Oh, I sort of wrote my bar a little off there. And dx dv, wait a minute, hold on a sec. Did I? Oh, I wrote arc. I wrote something sort of crooked. Oops. Let me just fix this real quick. I shouldn't have written it like that. I should have written it like this. Sorry. Okay, that's better. Dx dv, dz dv. Whoops, that's a y. Okay. And then if you were going to be looking at something more complicated, so instead of f being a function into R, codomain R, if it was, say, into R2, then you'd have a couple of component functions, an f1 and an f2, and you'd have a second row in this first matrix here, and so on and so forth. Now, we won't need anything that complicated for this class. And in fact, you might choose to think about this in a somewhat simpler fashion using the following tree diagram. So this is sort of to map out the dependencies. So we have f, and f depends on x and y and z, and then x depends on u and v, and y depends on u and v, and z depends on u and v. And then when you go to compute one of these chain rule terms, so if you're doing the derivative of f with respect to u, you need the way that f depends on u through each of its branches. And then those three branches, those are exactly the things that you see showing up in this term right here. And then similarly, if you want to do how f depends on v, then you use chain rule using these terms here coming down the other side of the branch of the tree, and that gets you all of these ones right here. And so, yeah, maybe I should explain just a little bit more. So this segment right here represents how f depends on z, and then this one right here represents how z depends on v. So that's telling you that you need the term df dz, dz dv in your summation, and that's of course what happens right here. And then you would also need to include the product of these two and the product of these two, and then that would give you the whole thing.